Educator Carlos Plain of Durham School states, "Absolutely, I went through my whole time on Earth enabling an explicit speculation of the universe. Moreover, at last, the speculation is being endeavored. I invite that because that is how we push ahead. That is the manner by which we make progress in science." The James Webb Space Telescope is disturbing an extraordinary amount of what has been viewed as truth in cosmology. For the new year, another ultra-deep picture shows that we have serious goofs in cosmology. The telescope, which was supposed to show us the basic stars of the universe, is changing into an adversary of the past viewpoint and may present to us a totally amazing science. Not all specialists are grappling in fear at the new realities. Other well-informed authorities welcome the advancements since it has, for a seriously prolonged stretch of time, been sure that something was the matter with our old hypothesis. The deviation in the evaluation of the advancement speed of the universe alone ought to have shaken experts' perceptions eventually in the past, yet bringing everything into account, they adhered to old hypotheses. The astronomical microwave background radiation, CMB, considered the most settled light in the universe, was made something like 380,000 years after the Big Bang, at the point when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Scientists call this process reionization, which made the universe transparent to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were managing another kind of radio-receiving antenna technology. This discovery was for quite a while seen as possibly the most grounded piece of evidence for the theory of the ancient Big Bang, earning Penzias and Wilson a Nobel Prize and an undeniable spot in the history of stargazing. The CMB most likely offers a perspective on the early universe with little temperature differences, giving basic information about the circumstances not long after the Big Bang. Specialists involved the CMB as a strong scratching of the vital evaluations of the material universe to check the advancement speed of the universe, among other things. The cosmologist Edwin Hubble had previously settled this in the late 1920s, finding that far-off galaxies retreat from us and that their speed is proportional to their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble didn't have the high-level assessing strategies available many years later when the CMB was discovered, which led to a recalculated expansion rate. These were by and large lower than Hubble's original figure. Later, specialists recalculated the rate once more using type Ia supernovae as standard candles, providing stable light that could be used as a reliable measuring point. The evaluations inside the CMB yielded an expansion speed of around 67 kilometers per second per megaparsec, while estimates using cosmic explosions yielded around 74 kilometers per second per megaparsec. What does this disparity in determining the development speed of the universe really tell us? Did you figure out that this goof has been known since the 1990s? Since that point, examiners have known or at least thought that something might be the matter with the appraisal of the CMB, the assessment methods, or the prospect of the universe's expansion. The irregularity between the noticed and expected values of the expansion rate is referred to in science as the SAA tension or Hubble strain. The implications of this strain are huge, showing that essential pieces of how we comprehend the universe might be defective. For quite a long time, experts were confounded. Since the James Webb Space Telescope went into operation, it has furnished specialists with shocking data that may now uncover information on the issue of the development speed of the universe, with systems so old and mature that their development ought to have started theoretically before the Big Bang, overturning old cosmology. Researchers no longer talk about slip-ups or assessment contrasts. They talk about the crisis in modern stargazing. Not only might the development rate be off course, but the whole thought of movement or the Big Bang itself is being called into question. Pictures from the telescope give evidence of a universe entirely unexpected from what we have long thought. The SAA pressure was the principal censure to experts who still have faith in old hypotheses. Now they deal with an issue. Do we really comprehend the universe? Other scientists stand on the remains of their once brilliant source of both discovery and torture, investigating space with dread and grappling with what they find. Considering the crisis in science, we ought to ask ourselves, what do we really have some familiarity with the universe? To answer this, we really need to grasp how science functions. Speculative specialists use an intricate arrangement of numerical models, cautious data, and intelligent thinking to move conclusions from the general to the particular. Their understanding comes from a mix of perception, attributes, major results, and speculative assessments. The term theory alone shows that these are developments and thoughts, not outright pieces of knowledge. The main significant information we have are the photos telescopes give, the sound waves and radiation gathered with radio telescopes, and the latest data from neutrino surveying frameworks or gravitational wave indicators. With the James Webb Space Telescope, we now have an instrument that can split the light into individual frequencies and analyze it in remarkable ways. Webb can show us the basic parts of galaxies in the early universe billions of years ago, how much mass they contained, and the number of stars present. It can also follow the shape and course of a galaxy's development. Webb, however, has limitations. For instance, it can't constantly absolutely determine whether we are seeing galaxies or alternatively black holes with huge gravitational forces that emit as brightly as a galaxy. We must face the truth that our science has long accepted an inordinate number of potential results as facts, while dismissing alternative explanations. Research has for a long time been sure about its precision. The latest discoveries from the James Webb Space Telescope are essential clues to replace hypotheses with new insights, as has happened generally in science. Analysts are enthusiastically anticipating the new revelations, which are suddenly astonishing and diverse. Experts are attempting to develop new explanations. The new discoveries shake the underpinnings of our current science, upsetting many experts. The current models of genuine science are still largely based on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the foundation of our comprehension of the reality of this world and the universe for a long time. Newton's principles make sense of the movement of things under normal circumstances and function especially on the planet. However, in space, his speculations required development, generally carried out by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, changed how we interpret reality, showing that time and space are relative to one another and depend upon the observer's motion. His general theory of relativity, published in 1915, expanded this idea with mathematical descriptions of gravitational attributes based on the curvature of spacetime by masses like stars or galaxies. Einstein's principles and thoughts were profound in many areas. However, he too recognized their limitations. He knew his theory would never fully describe the universe and longed to see a unified theory, which he never achieved. No other professional has reached this stage either. Wouldn't it be intriguing to know where it lies? Michio Kaku, a prominent astrophysicist from the USA, said in an interview that addressing this issue would certainly win a Nobel Prize. Might we explore whether the specialists may have missed potential misinterpretations or whether our telescopes are to be faulted? Dark matter and dark energy are at the top of the suspect list for the fundamental reasons for the cosmological crisis. Our evolving models of the universe incorporate ideas that dark matter and dark energy make up around 95% of the universe. However, neither has been clearly observed, and their confirmed presence has never been demonstrated. They probably don't exist in any form or shape, requiring alternative explanations for the universe's expansion and the dynamics of galaxies. On the other hand, they could have properties we don't yet comprehend. One idea is that the true properties of dark matter and dark energy have changed over time, possibly showing some form of evolution. Gravity is another theory to be tested. This force, which creates attraction through mass or curvature in spacetime, has not yet been fully explained. The concepts of spacetime curvature, which originate from Einstein and have been traditionally supported, may require revisiting. We can't dismiss the possibility that gravity has unforeseen properties or that another force is responsible for the gravitational attraction between objects over time. A few constants have been established in cosmology and astronomy as universal principles. The study of the universe has always been a journey defined by our constant search for understanding and discovery. From ancient human civilizations observing the stars to current space telescopes exploring the depths of the universe, each step in development and theory has revealed new secrets while challenging established beliefs. In the field of cosmology, the James Webb Space Telescope, JWST, remains as a beacon of our scientific progress, promising to change how we interpret the universe's beginnings and development. Launched with outstanding capabilities, JWST represents a leap forward in observational space science, designed to look further into the universe than ever before with unprecedented precision in studying radiation. The CMB, often referred to as the glow of the Big Bang, offers a perspective on the universe as it existed only 380,000 years after its first interaction with the world. This ancient form of radiation conveys essential information about the universe's early conditions, including its temperature variations, which are critical to understanding the development of galaxies and large-scale structures. The disparity in the determined potential values of the Hubble constant, known as the Hubble strain, has been a subject of prolonged debate. It suggests that something is off with our basic understanding of the universe and its early networks. Discoveries challenge traditional theories and call for a reassessment of whether our perspective on cosmic development is fundamentally flawed. New insights may uncover hidden parts of the universe's creation, raising questions about dark matter and dark energy, two unexplained components that make up most of reality. The advancement of science depends on the ability to reshape our theories based on new information. Webb's mission epitomizes this pursuit. Its discoveries will serve as a foundation for future cosmological discussions and should ignite new perspectives on the universe's mysteries. The future of cosmology may witness significant changes, leading to profound implications for how we interpret the universe, from the Big Bang to the ongoing cycles that define its fate. The answer to the greatest infinite question may lie beyond our current knowledge, and Webb's observations may ultimately be essential in uncovering new insights that could reshape how we interpret reality itself. The path ahead for cosmology and space science is filled with potential. Each new observation and piece of data from telescopes like Webb brings us closer to answering the most profound questions humanity has ever posed. How did the universe begin? What is its ultimate fate? Are there other forms of life out there? Or are we alone in this vast cosmos? These are questions that may one day find answers, and the James Webb Space Telescope is at the forefront of this monumental effort. The future of cosmology will likely involve a fusion of new technologies, refined theories, and groundbreaking discoveries that continue to push the boundaries of what we know. As we venture further into the unknown, one thing is certain. Science, like the universe itself, is always in a state of constant expansion, driven by the pursuit of knowledge, understanding, and the wonder of discovery. As the James Webb Space Telescope, JWST, continues to capture unprecedented data from deep within the cosmos, it raises profound questions about the fundamental nature of the universe. While traditional models have served as the foundation for much of cosmological research, the new insights revealed by JWST suggest that the cosmos may be even more complex and mysterious than we have imagined. These revelations invite us to reconsider not just the mechanics of cosmic expansion, but the very fabric of space-time itself. One area of focus is the early universe, which, according to current theory, underwent rapid inflation shortly after the Big Bang. JWST's ability to peer into the farthest reaches of space, closer to the universe's origins, promises to shed new light on this tumultuous period. By observing the formation of the first galaxies, stars, and black holes, scientists hope to better understand the sequence of events that shaped the universe's structure. The high-resolution images JWST produces could allow us to detect structures that were previously invisible to older telescopes, offering clues about the initial conditions of our universe. This ability to look back in time is what makes the telescope such a game-changer. It's not just about observing galaxies and stellar formations as they exist today, but reconstructing their earliest stages, when they were still in their infancy. These observations will challenge the standard cosmological models, which rely heavily on the assumption that the universe is homogeneous and isotropic at large scales. The finer details revealed by JWST may show that the universe is more irregular and dynamic than we thought. Another area of exploration lies in the behavior of gravitational waves, a phenomenon that was first predicted by Einstein and confirmed a century later. While we've made incredible strides in detecting and studying gravitational waves, there's still much to learn about their role in shaping the cosmos. These ripples in spacetime carry information about some of the most violent events in the universe, such as the collision of black holes or neutron stars. As these waves propagate through the cosmos, they provide a new layer of information, one that could open the door to understanding exotic phenomena that are not easily detectable through traditional light-based observation. Moreover, JWST's ability to explore exoplanets, particularly those located in habitable zones, could dramatically shift the course of the search for extraterrestrial life. By analyzing the atmospheres of distant planets, scientists can look for chemical signatures, such as oxygen, methane, and carbon dioxide, that could indicate biological processes. This marks a significant step forward in our search for life beyond Earth, opening up possibilities for understanding whether life might exist elsewhere in the universe or whether Earth remains truly unique. The findings of JWST also challenge long-held ideas about the distribution of matter across the universe. The theory of cosmic inflation, which suggests that the universe expanded exponentially in the first moments after the Big Bang, has long been supported by observational data. However, the latest images and data from JWST may point to new variations in the inflationary model, or even suggest alternative explanations for the distribution of galaxies and dark matter. As scientists continue to analyze these results, we could see a shift in our understanding of both the origins and the large-scale structure of the universe. In addition to these cosmic puzzles, JWST's insights are prompting a rethinking of dark matter and dark energy, the two mysterious forces that make up most of the universe's mass and energy content. Despite decades of research, both remain largely theoretical, and their true nature is still one of the greatest mysteries in physics. New observations from JWST may provide clues that could help uncover the true identities of these elusive substances, potentially leading to revolutionary breakthroughs in our understanding of the universe's fundamental components. The continued exploration of space is not only a pursuit of knowledge but also a reflection of humanity's inherent curiosity and desire to push the boundaries of what is known. Each new discovery opens up more questions and challenges our existing models. As we continue to probe deeper into the cosmos with tools like the James Webb Space Telescope, it is likely that the answers we seek will not only reshape our understanding of the universe but will also transform the very way we view our place within it. The universe is vast, and our journey to comprehend it is just beginning.